Hi, good news! Dr. Lewin responded to my previous video with 3 new videos. Science time! But before getting to the science, let's address the drama a little. So I made a video disagreeing with Dr. Lewin, a scientifically well-decorated ex-professor at MIT. The disagreement was on that Dr. Lewin said Kirchhoff voltage law or KVL doesn't hold when magnetic fields are involved. The first 2 video responses Dr. Lewin made were explanations as a response to the flood of my viewers commenting under his videos. Maybe he made those videos without watching my video.
The rumor has it, but it's only a rumor, a person who says he has a master's degree makes the following statement. The entire reason Dr. Lewin was reading 2 different voltages was due to bad probing. Such a ridiculous statement. I have not been able to find that video. And it may not even exist.
I feel like he's telling me he actually watched my video, but to save me the embarrassment, I should remove my video. Anyway, Dr. Lewin didn't find my video amusing. He assumed I don't agree with Faraday's law and I don't agree with his measurements. And in the comments he said that my video is dedicated to discredit his lectures and is insulting. And an embarrassment considering I have a master's degree.
It is equivalent to saying the earth is flat.
No, not flat earther. Call me an idiot, but not a flat earther. It is fine, people. I don't have any problem with Dr. Lewin. Please don't try to defend me by bothering the man. Well, if you watch my previous video, you'll see how much I actually agree with Dr. Lewin. I would never try to discredit his lectures for no reason. He has around 300 lectures in his channel and I suggest everyone watches them. They are great. In the process of this back and forth, a lot of people left comments, with majority of them being pretty respectful to both sides. But there are always these oddballs who leave bad comments. I'm sure Dr. Lewin received his fair share of unnecessary bad comments from my viewers, as I did from his fans. Here's a few of them written for me. Obviously, the balding skin with a single eyebrow does not understand potential theory in non-conservative fields. ElectroBOOM, shut up on the topic. Didn't you take an applied electromagnetics class in your EE degree? As another EE, I'm embarrassed for you. And when I left a comment under Dr. Lewin's video, somebody said, "Don't worry dude, pray to Allah, He will solve your problem. Go to a mosque nearby, He knows KVL better than this Walter Lewin. Moreover, both Kirchhoff and Faraday are in heaven, so just request Allah to ask them for a solution." And my hero Ion Kasu said, "What the hell is wrong with you, boy?" I chuckled. Both of us chose to live on the internet and should deal with the consequences. Personally, I don't care about bad comments, but I do apologize to Dr. Lewin for receiving a similar wave. That wasn't my intention. It's not a political debate and we are not looking for votes. It's about science and facts, and in science we don't need people who blindly follow somebody. We need people who put their preferences aside and look at hard facts and judge accordingly. In his 3rd video, although he still didn't agree with me, which is totally fine, Dr. Lewin did a good job of calming both sides down, allowing for a more civilized discussion, and I appreciate it. That's the end of the drama. But don't leave now, hold my hand. Let's go through this journey together. It's a long and tough journey, but coming out of it, we will learn much more. Let's do it. So as Dr. Lewin suggested, I contacted his ex-colleague, Professor John Winston Belcher, a current MIT professor, a great man with his own series of scientific awards and achievements. He spent so many hours with me on this and made this beautiful MIT quality report, which I share with you in the description. I'll get to that a bit later. Now let's go all the way back. If you have watched my ElectroBOOM 101, I showed that voltage is basically defined as the amount of potential energy available to move unit charge, or V is equal to the energy acting on charge divided by charge. And of course, work or energy is equal to the force applied to the charge times the distance that the force travels with the charge. Now what happens if the charge moves in a closed loop in the presence of this force? It is like gravity. It doesn't matter if you move sideways because the gravity always points down. The mass will lose its potential energy as it gets closer to the Earth and will gain the same amount back when you return to the same point. So the sum of all energies stored or produced by gravity is 0 in a closed loop. Basically, you take out only what you put in. That's called the law of conservation of energy. For the same reason, the sum of all energies acting on the charge in a closed loop must be 0. We can divide these by Q to get voltage. And we arrive at the original definition of Kirchhoff's voltage law. Some people call him Kirchhoff, I call him Kirchhoff. It is based on the law of conservation of energy and says at any point in time the sum of all voltages in a closed loop must be zero. Let's create an electric force. You know, if we have a tiny charge q in the presence of a stationary big charge q, there will be an electric force between them, repelling or attracting depending on the polarity. Let's assume they attract. For the sake of simplicity, I'll avoid vector and curl math. Let's keep it simple so it's easy to understand. According to Coulomb's law, this force is equal to some constant times the tiny q times the big Q divided by a square of their distance. The tiny q starts moving due to this force. Let's assume charge q moves by a very small distance of delta L, where we can assume the force almost remains the same, because like I showed, force is a function of distance. So the work done with that force in that tiny distance, or delta W, is equal to the force in that spot times the distance. For extremely small distances, we can write this as dW equal to the F times dL. And if the charge moves a distance of L from point A to B, to get the total energy or work, we integrate the energy, which is integral of F dL from point A to B. So the voltage between points A and B would be that energy divided by Q, or integral of F dL divided by Q. Q is not a function of L, so we can take it inside, and electric force divided by charge is defined as electric field, which is equal to a constant times Q divided by a square of distance. And from these we conclude that voltage from point A to B is equal to the integral of E dL from point A to B. And like I said before, if we move the charge in a closed loop, the sum of all energies and so all the voltages in the loop will be zero. So in an electric field only, the sum of all voltages is the closed loop integral of E dL equal to zero. Later on, Michael Faraday revolutionized our understanding of magnetic fields, and with the help of James Maxwell, they came up with the Faraday's law and Maxwell's equations. I, of course, fully comply to those laws and have nothing against them. According to Faraday's law, if we have an open surface surrounded by a closed loop, the closed loop integral of E dL, which is a voltage generated by electric fields around the loop, also known as electromotive force, is equal to the rate of change of magnetic flux phi through this surface in time. And this magnetic flux is all the B magnetic fields passing through the surface enclosed by the loop, and is equal to the magnetic field times the surface area. Remember, I showed in the presence of electric fields only, the closed loop integral of E dL is zero. But as soon as we have magnetic fields through the loop, this won't be zero anymore, and we have to follow Faraday's law. Now, watching Dr. Lewin's first response video, I noticed that he believes this to be Kirchhoff's voltage law.
Kirchhoff's loop rule is that the closed loop integral of E dot dl is zero.
If that was in fact the definition of KVL, I would 100% agree with Dr. Lewin that it is a special case of Faraday's law where d phi over dt is equal to zero, which means there are no magnetic fields. But that's not the definition of KVL. KVL says that the sum of all voltages in a loop must be zero. But then you might say that the voltage is integral of E dL. But that's not true. Voltage is any energy per unit charge, not just energy from electric sources. Is that it? Does Dr. Lewin believe that voltage is only defined by electric forces? Because looking at his second response and other videos, it seems he doesn't think of d phi over dt as a different entity.
Newton's second law, F equals ma.
You see, he's showing F minus ma equals 0 is the same as F equals ma. What he's trying to explain is that in this equation, force is equal to mass times acceleration. Ma is just the value of F and is not a separate entity. So writing it as F minus ma equals to 0 is pretty pointless, which is true. But similarly, he thinks that minus d phi over dt is only the value of this integral and is not a separate entity. But that's not true. These two are two different entities that exist in a circuit with their values equal in a closed loop. Like when you balance your weight with your friend on a seesaw, the value of your torques is equal, but you are two different people. But it returns to the definition of voltage. What if voltage is defined as the effect of electric fields only? Now I know that Dr. Lewin defines it like that, and with that definition, all his videos make perfect sense. But who's right? In his second video, he refers to a paper written by Robert Romer, published in American Journal of Physics back in 1982. I read the paper and have a copy of it in my description if you're interested. It's a great paper focused on what the meters would measure, based both on math and actual experiments, and they both match, and also they match Dr. Lewin's experiments and mine. What Romer does is that, like Dr. Lewin and I, he has a loop of wire with two different resistors, one at each side, and a changing magnetic field passes through the middle. And also he has two identical meters connected across the same point in the circuit, shown as these resistive components. He imposes some specific conditions on his setup and shows that meters read different values. Each meter reads the voltage across the resistor on their side. I did the same experiment in my previous video and showed that it was true and provided some explanation. In my setup, I had to impose my own conditions because, unlike Romer, my coil was pretty small, so the fields could close before passing the main loop, or could create uneven fields. So in my setup, the condition was that the probe wires had to run very closely to the loop wires to make sure they are exposed to the same magnetic fields as the main loop, which is the same idea as in Romer's setup. Now I can easily explain it mathematically. This is also explained beautifully in Professor Belcher's document he created. He provides such great detail that you can see how the charges move in the loop with your own eyes. In my setup, I twist the wires at this point all the way to the scope to make sure that the scope and this extension of wire are not affected by the field. But for calculations, we can model the scope as this tiny resistive component across these points. The scope resistor can be 1 mega ohm, and our loop resistors are much smaller in kilo ohm range, and the connecting wires have insignificant resistance, we can assume 0. If the field is going through the page that way, the induced current is this way. According to Faraday's law, the closed loop integral of EDL over the main loop is equal to minus d phi over dt, the change of magnetic flux through the loop. We can split this integral into two pieces, one from A to B and one from B to A. We know that the integral of EDL over ideal inductors and wires is 0 because they have no resistance and only work with magnetic fields. So the integral of EDL from point A to B is only the voltage across resistor 1, and from B to A is only voltage across resistor 2. So we get VR1 is equal to minus d phi over dt minus VR2. Now if we go through a different loop through the probe wires and the scope on this side and main loop on the other side, we get a similar thing, that the scope voltage on this side is equal to minus d phi over dt minus VR2 because the same flux passes through all loops. So basically the voltage of scope 1 is equal to VR1, and based on similar calculations on the other side, voltage of scope 2 is equal to minus VR2. Math matches our readings. I never disagreed with Dr. Lewin on this and confirmed it in my previous video. In his paper, Romer never disputes KVL, but in a section titled Voltage across an inductor, he expresses his confusion and discomfort around what happens to the fields in an inductor. Then he mentions two books that helped him find peace. One of those books is the Feynman Lectures on Physics by Feynman, Layton and Sands. If you don't know Dr. Feynman, you should really check his Wikipedia page. He was a fine man, pun intended, a huge scientist and an all-round great guy with many contributions to science. Both Professor Belcher and I read Romer's paper and chapter 22 of Feynman's book on AC circuits, and we also found peace. Let me explain. The book explains that for every component, like an inductor or a capacitor, it is best to use a lumped model, meaning that all the fields are contained within the component and don't leak outside. Doing this makes it easy to calculate the voltage across the component. And the voltage across the inductor is minus L di over dt, despite the fact that the integral of EDL through the inductor is 0. This is a real voltage across a magnetic component, and doing so, the book shows that the sum of all voltages in a loop is 0 and KVL holds. So Professor Belcher also concluded that Dr. Feynman himself and I have the same definition for voltage, and the KVL holds in all cases. Although maybe I shouldn't assume myself at the same rank. But then you might ask, if KVL and Faraday's law do the same thing, why do I push for KVL? It's because KVL is much easier to work with over time and frequency domains. See, if we have a circuit like this, knowing that KVL holds, it's very easy to calculate the circuit impedance, which is that resistor in series with these two in parallel, which is the impedance of the inductor times impedance of the capacitor over this plus that, which is equal to that. I can easily calculate my LC resonance frequency by finding where this becomes zero. I just replace S with j omega and calculate my frequency. Feynman book explains that by making suitable approximations in a lumped model, it is possible to ignore the great complexities of the fields inside the object. A separation is made between what happens inside and what happens outside. This is important to know because even if the fields are not contained and leak outside, we still have an inductor and defined voltages everywhere and KVL holds. But this creates huge complexity in our calculations because now the leaking fields affect all the components and wires in the circuit that we have to take into account, which is almost impossible because now there are so many new variables introduced that we might easily overlook. Our simple loop and probe was the easiest example of uncontained fields. The fields close around the entire circuit and affect everything. Every piece of wire and even the resistor itself becomes an inductor and the secondary of a transformer. One of the examples people brought to disprove my conclusions was that what if the entire loop was made of a uniform resistive element, and we take these 2 points and the induced current I would create 2 different voltages across the same points based on Ohm's law. What you must understand is that a real resistor is only ideal if it's infinitely small. As soon as it has any dimensions, it at least has an inductance series with it, especially something this long. Remember, to make it easy, you have to produce a model using lump elements. You pull out the resistance and the secondary inductance and put them in series for each half of the circuit. If you assume a uniform field through the loop and D1 and D2 are the length of each side, this is what you get, and a known voltage across these points and KVL holds. There is an interesting experiment in one of Professor Belcher's assignments that kind of looks like this and shows the effect of uncontained fields. We have an AC supply in series with a resistor and a loop of wire, and on this side we measure some voltage and on the other side we measure 0 volts. Here's what I have. The supply connects with these alligator clips to this resistor and the loop, and I'm measuring across the loop with these wires. When I'm probing on the power supply side, I read around 40 millivolts. And now if I move the wires to the other side of the loop, I'm reading 20 millivolts instead of 0. It's half of the previous voltage. I should read 0 volts, but instead I'm reading half of this voltage because I introduced a new probing problem. Both my AC supply and probe are coming from the same scope. See if you can figure out what's going on. On the other hand, if I create an inductor with contained fields like winding around the toroid core, all the fields are contained in the core and my readings are not affected by where I probe. Here I replaced my loop with a toroid and a few windings, and you see, it doesn't make any difference if I probe on this side or the other side. Okay, let me explain why we didn't read 0 on the first test. If our AC supply and the probe are isolated, of course we read 0 volt there. A simple engineer like me would explain it by the fact that every piece of wire is an inductor. If we have a voltage V induced on the main loop, we would also have half a V induced on equal length of probe wires exposed to the same fields that subtract from V, and we read 0 volt difference there. A more proper scientist like Romer would say that the scope voltage is the integral of EDL over the main loop on the scope side, which is 0. Now in my setup, the AC supply and the scope ground are not isolated and shorted through the scope. The simple engineer would say, oh sure, you just shorted across that voltage on one of the probe wires, so the scope would read half the voltage. That's not wrong, but it's a bit misleading. What if we short across the probe wire with a piece of wire that runs closely to the probe wire? It doesn't make any difference and we still read 0 there, because the fields close around all of them. The more accurate reason is that the ground through the scope creates a large loop. If phi is the magnetic flux through the loop, half of it closes on the top side through air and half of it on the bottom through the ground loop. So like the case of toroid where all the fields were contained in the core, here the majority of the fields are contained around the probe wire and are too far to loop around the shorting ground wire and affect it. This is as if the probe wire is an inductor shorted by a piece of wire. There is still current running through it, but the voltage across it is zero. This is how we are shorting the induced voltage across the bottom probe wire and read half a voltage at the output instead of zero. You can of course write the Faraday's law around the loops and get the same results. Thank you, Professor Belcher, for helping me with this.